Here's another example. So find the derivative of this function. So again, this is that area generating function. You have the variable, a function of the variable up here is the upper limit. And our function f of t is t over 1 plus t cubed. So this is a little bit more complicated because this upper limit's not just x, it's a function of x. So it's really a composite function. So I can think of it like this. If u is 3x plus 2, u of x, my given integral is y of u. It's the integral from 1 to u. So since y is actually a composite function, we're going to use the chain rule along with the fundamental theorem of calculus. So the fundamental theorem of calculus tells me that the derivative of this with respect to u is f of u. And the chain rule tells me I need to find the derivative of the inside function and then multiply them. So here I have the derivative in terms of x only. There's a second part to the fundamental theorem of calculus, and that is a way to help us evaluate definite integrals without having to use the limit of Riemann sums. So the first part showed us the relationship between that area generating function, which is a definite integral, and the antiderivative. So this part says, all right, if my upper limit is another constant, now it's not a variable anymore, I can evaluate this definite integral by finding any antiderivative of f and then evaluating it at the upper limit, evaluating it at the lower limit, and then subtracting. And f can be any antiderivative. So remember, there were most general antiderivative is when you add that constant c, and then a particular antiderivative is when you're given a value so you can determine a particular value of the constant c. Here, with a definite integral, we don't need to worry about the constant c because it would subtract out when we subtract f of a from f of b. So that's why it says capital F is any antiderivative. And I wanted to warn you about the notation. So I use Desmos for these slides, and it does not have a vertical bar where you can have an A at the bottom and a B at the top. So I had to get that look by these square brackets with A at the bottom and B at the top. So the notation f of x with a B up here and an A down here means evaluate f at the upper limit, evaluate f at the lower limit, and then subtract. So if you think back to section 4.9 when we talked about antiderivatives, if you remember, we saw that the distance function, when our object is going in just one direction, is the antiderivative of the velocity function. So this is should be kind of familiar if you think about that. So the antiderivative, the indefinite integral of the velocity function, is just the distance that you've gone, s of b minus s of a. Here's an example here's a definite integral, and we're going to evaluate it without having to use limits of Riemann sums. So I find an antiderivative of x to the 100. Well, using the power rule, it's just x to the 101st over 101. So there's my antiderivative. And then I'm going to evaluate it at 1. I'm going to evaluate it at minus 1. And I'll subtract f of minus 1 from f of 1. And I get 2 over 101. So it's a lot easier than trying to figure out limits of Riemann sums. Another example, the definite integral from 0 to 1 of 1 plus r cubed dr. So we'll see there's a much easier way to do this with substitution in a section or two. For right now, it's actually easy enough to figure out this integral. If we expand that 1 plus r cubed to get this polynomial. And then we integrate term by term. So it's the integral from 0 to 1 of just 1 times dr plus the integral from 0 to 1 of 3r squared plus 0 to 1 of 3r, etc. So looking at each of these individually, the integral from 0 to 1 of dr is just r. And then when I evaluate it at 1 and I evaluate it at 0 and subtract, I just get 1. From the integral from 0 to 1 of 3r squared dr, I factor out that 3, and I'm just left with the integral from 0 to 1 of r squared dr. Using the power law, I add 1 to the exponent, divide by that, and then I evaluate that antiderivative at the limits of integration and subtract. And again, I get 1. So continue on using the power law, and then adding up each of these integrals, I'm going to get a value of 15/4. Example 6. Remember that antiderivative for the exponential function, if it's not base e, is just that function divided by ln of the base. So an antiderivative of 2 to the s is 2 to the s over ln of 2. And then I evaluate that antiderivative at 4, evaluate it at 0, and subtract. The last example, also from homework problems, use a graph to give a rough estimate of the area of the region that lies beneath y equals the cube root of x. Then find the exact area. So you can look at each of these. So here's 27. You have 27 units along the horizontal axis, the x-axis. And like if you look at y equals 1, you have almost 27 rectangles of width 1 filled in here. So this is about 27 times 1. If you look at between y equals 1 and y equals 2, there's about 21 of these rectangles shaded in under the curve. Look up here from 2 to 3, here's 27, here's 10. So this is 7 rectangles. This is 10 rectangles across, but they seem to be just about half shaded. So I'd say 5 plus 7 is about 12. Again, this is just an estimate. So summing this, you get 60. Of course, that's annoying to do. It's a lot easier to get the exact area with a definite integral. X goes from 0 to 27 of x to the 1/3 dx. Get the antiderivative, evaluate it at 0, evaluate at 27, subtract, and I get 60.75. So the fundamental theorem of calculus just gives us an easier way to determine definite integrals, and it makes a connection between the antiderivative and the area function for a function f.